Okay, here we are at our first stop. This is the Dean Creek elk viewing area. Yesterday on the in-person trip, the elk were kind of right over here. I am not seeing them as close today, but we'll talk about that in a minute. The first thing we're going to look at here, though, is the shape of this valley that we're in. Just on the other side of the highway sits the Umpqua River and a fairly deep channel. So if we were to look across this valley, we have a steep hill, a deep channel, and then this broad, flat area before we have relatively steep hills again. What this tells us is this story of tectonic uplift in this area. This flat area here is because our river at one time was sort of meandering back and forth across this entire valley bottom. Eventually, though, our coast ranges uplifted enough that our river was forced to cut down in the new place over here. This is what we call trying to establish a new base level. As our Pacific plate subducts underneath our North American plate, it's sort of bulging up this edge of the North American plate, uplifting the western edge of the North American plate, lifting everything up here. What goes up must come down. So our rivers move around when they're kind of at a nice steady state. They're trying to run downhill, but it's basically flat anyway, so they'll go in lots of different directions. Then when we lift everything up, suddenly sea level, the level it's trying to get to, is relatively lower, and we get erosion where it's cutting down, weathering this material and eroding it away. So that's our big geology start for thinking about this trip here. We have steep, big channel, this flat, what we call river terrace, that is a record of our uplift. Now let's bring in the invisible elk as part of what we're going to talk about as well for this trip. So elk are kind of an interesting animal. They're a member of the deer family. They're quite large. But what's cool about them is that we can also think about how climate and landscapes have changed through time. We don't get elk coming into North America until 10 to 12,000 years ago, this very, very end of the Ice Age, when a lot of our big animals in the Ice Ages, our mammoths, giant camels, horses, and things like that, are going extinct. Elk are browsers. They like to eat a mixed variety of plants, a lot of different leaves, things like that. Whereas some of these more cold adapted open area animals, our horses, our camels, were grazing. They were eating a lot of this sort of tundra near our big ice sheets. So as the ice retreats, elk are one of the things that invades into North America. So they're this neat story, and that they can kind of track these changing climates, changing landscapes, and the extinction of other organisms within these ecosystems. So they are relevant to the geology. I'll add in some photos of them when they're closer. Bonus bit of elk. SWOCC also has one of the oldest elk jaws as a fossil as part of our fossil collections. Okay, here we are at our second stop. This is the Scottsburg County Park. It's a boat launch area. But we've got a great view of the Umpqua River as well as some of these local rocks. So let's take a little bit closer look at some of these rocks. These were brought in, but they are local. What kind of rock do we think we've got here? It's relatively dark in color. We can't really see much in the way of individual crystals in any of these rocks. Pretty gray. This is going to be basalt that's got a few other little things added onto it, but it's also basalt that didn't have very much gas in it. So remember, we have solid, liquid, and gas that makes up what goes into our magma. This was basalt that didn't have a lot of gas in it. And this is going to be one of our really common rocks in this area. In addition to these volcanic rocks, we're also going to be getting into volcanic rocks that are interbedded, so alternating layers with a lot of our sedimentary rocks. Cutting through all of this is our Umpqua River. So here I am walking out the dock. Here's the boat ramp right here. We can think about the change in the shape of our valley. Now we have the valley much narrower than it was before, but we still have these river terraces. So if we look at where these houses are all along this far bank, we have this narrow shelf attached to the edge of the valley. This is another one of these river terraces. It's just a bit smaller. There's a little tiny one over on this side as well. That's going to be where the road is. Those are places that previously this river was able to meander back and forth across this valley, cutting that platform until the whole coast range was uplifted enough for the river to cut down again into this broad, deep channel that it makes up today. Right now, we are kind of at a change in the tides, so there's basically no movement. Even though this is a freshwater river, we are still in an area that as the tide comes in, it sort of pushes in on our freshwater, so we're not really getting a lot of movement. If I look at places where there's like a little leaf floating in the water out there, it's not really moving. Yesterday when we stopped here, we could still see current going out to the ocean. There's a better, very stationary leaf to show our current. This is going to be important for a later stop, that even though we have fresh water, we can still get this impact of tides. So we can think about how tides are interacting with our landscape. As an extra bonus, when I came here scouting for the field trip, I happened to see black bear just before the turnoff to this park. So here's a picture of one of our local wildlife. Our next stop, sorry for the highway noise, is these series of rather incredible road cuts that I'm just east of Elkton. We've come up over the crest here. So we've now changed the water divide. So we are in a different drainage basin from here on out than our whole rest of our drive this morning, coming up the Umpqua River. So looking at this outcrop, we have these beautiful layers of rock. One of our assumptions in geology, though, is that everything starts out flat lying. If these are no longer perfectly flat lying, that means that something tectonic has to have happened to move them around. You can also take a moment to look a lot closer at these rocks. Can we see grains, any individual grains in these? Occasionally, there's some little white bits. It's very sort of gritty feeling. This is sedimentary rock. We can see our nice layers. That tells us sedimentary rock, but it's very fine grained. This is smaller than sand size for the most part. I can't really see very many sand-sized grains, but when I feel it, it's still slightly gritty feeling. So this is telling me this is primarily silt-sized. We also get areas that are kind of reddish, yellowish showing up. These might be things like iron and sulfur that are reacting with oxygen. So likely to have somewhere where we have very fine-grained rocks. There's a fair amount of dark in them, which is often associated with organics, as well as this iron and sulfur. This might have been deposited in something like an estuary. So an area that we have a lot of plant material, we have low energy so that our sediment can settle out, even though it's quite fine-grained. But then over time, this has been uplifted and little tiny faults, so offsets in the rocks. It's been tipped up in different places. We've got quite a lot of variety to it here. We're going to start with a little description of this mammoth we see here in the courtyard outside of the museum. Okay, so this was a pretty fun story. I was actually on a field trip with University of Oregon introductory geology students. We'd taken them out to Eastern Oregon to a site near Fossil Lake, and students found these round depressions. Turned out those were actually mammoth tracks, and there was an adult mother mammoth and a small baby mammoth. The mother went in a straight line, the little baby sort of zigzagged back and forth all around where the mother's tracks were. So these statues were built as a homage to that particular field trip. What's really cool is during the pandemic, the entire permanent exhibits for the University of Oregon Museum of Natural and Cultural History exhibits were digitized. So there is a digital museum that you can visit and get to go explore all of it, sort of digitally walk through the museum. So I'd like you to take a little bit of time and do that, and take some time to look at especially that Explore Oregon, see what kind of fossils we used to have in the state of Oregon. Okay, our next stop is Skinner Butte. This is one of the hills or buttes, flat-topped area, that outcrops towards the north of Eugene. If you've spent any time in Eugene, as you can maybe see in this first picture, it's really close to REI, that kind of area. There's the Butte to Butte race. There's a lot of different reasons people come to the area. Rock climbing has historically been one of the big attention draws. There's quite a few different climbing routes that are set up there. They're marked in one of these photos here. And on any decent day that it's not pouring down rain, you can probably see people climbing if you stop by this exposure on Skinner Butte that is known as the columns. Now, what are the columns? The columns are actually what we call columnar basalt. So this is basalt, or lava rock, that has, as it is cooled, contracted in the same sort of way that you would pull a pan of brownies out of the oven. They're really smooth on the top, and they kind of contract in on themselves and develop cracks. Because they cooled relatively slowly, they were able to form these really uniform columns. These have sort of a hexagon or octagon top to them and form these really long columns that were perpendicular to the direction that we had the base and the top as this was cooling. This area was historically mined, which is why we're able to see the basalt columns in this one place. If you look at the historic photo, we can't see any of the columns showing because this was the original shape of it. This sort of pinched side dome making up Skinner Butte and the much larger Spencer Butte to the south is what we call a laccolith. So a laccolith is basically when basalt is trying to intrude through layers of the earth to make it to the surface to erupt and doesn't quite make it. Instead, it gets trapped below some very dense layer that it can't force its way through. And as it cools, it sort of pushes up, forming this blister of basalt. Over time, the sedimentary rocks that were capping it eroded away, leaving the much harder blister of basalt as all of these large knobs that stick out basically from Eugene all the way north to Portland. So if you're driving that I-5 corridor through the Willamette Valley and you see these domes of basalt, that's what they are. These are all laccoliths. Okay, so this is stop 6 on our field trip. We are in Mapleton. So we're a little ways inland of Florence. Just saw a nice little fish rise out there. And the reason why we're stopped on this lovely stretch of the river is because this comes back to this story of tectonics and measuring how much the Oregon coast is uplifting. So we have the river right here. This is going towards the ocean. Notice though the direction our current is moving. It's actually going upstream right now. So this is all fresh water, but this is because of this change in tide. So as the tides come in, they're sort of pushing this water back up. And we can really consistently look at sort of averaging, knowing precipitation and things like that, this change in water level dependent on overall changes in sea level. Now, in most parts of the world, if we look at, if I have a graph that I draw with my fingers right here, if we look at sea level elevation on our y-axis, and on our x-axis we have years from longer ago to now, most places we're having this increase in sea level. If we measure relative sea level here in Mapleton, one of the places they're actively doing this, we're actually getting this relative decrease in sea level. So if we take the global sea level change that we know is happening from measuring it in lots of other places, including Seattle and San Francisco on the west coast here, we can tell that the Oregon coast is lifting up so high that even with that increase in sea level as well, we're uplifting our actual landform here, the whole coastline, faster than sea level is rising. So this is one of these really important places for measuring kind of how fast that uplift is happening. Because again, that uplift of the Oregon coast ranges is happening because of the subduction of the Pacific plate underneath the North American plate, sort of pushing all of this up. That total amount of stress that's accumulating is really important for predicting when we might have a Cascadia megathrust earthquake. The other thing that's kind of cool here is across the way we can tell that there was a fire a while ago, and it sort of cleared things up a little bit. We have this great outcrop of sandstone visible over there. So this is the Tyee Formation, and it is what we call massive, so it doesn't have a lot of individual beds in it. We can kind of see one little bed coming along here, but mostly it's just this whole lot of sandstone. It's relatively fine grained, it's kind of mixed in with some muds, and this is something that needs to not have a lot of energy in order to be deposited. So this isn't even beach sands, was deposited a ways out into the ocean. So this entire area has been uplifted enough that at the time, tens of millions of years ago, that the Tyee was being deposited, it was underwater in the ocean, and we've now uplifted this enough to expose all of this. So we can look over here at this marina, these sort of set pillars that go down and don't change in height. This is so your docks can kind of rise and change with the water, but there's monitors installed on some of these to take these measurements to get at this changing sea level relative to our changing elevation of our coastlines here. And this is one of the boat ramps here on a lovely sunny day. Okay, our final stop of the trip is the Exploding Whale Memorial Park. This is one of Oregon's newest state parks. Now, the first thing we did at this site was we walked down to this confluence where a river meets the ocean. And it's got this neat area where our shifting currents push sand along and make this sort of circuitous route for the river to actually meet the ocean. We're collecting a lot of sand in this area, both sand that the river is transporting along and that the ocean waves are pushing along and that wind is forming into dunes. So we have 3 different methods of moving sand around. Stop and think for a second about which one of these is going to take the most energy. Probably a big storm in our ocean is going to have the most energy and can move some of the larger grains. But also our rivers, if they're at a flood stage, a lot of water coming out of them, are going to be able to move a lot and larger and heavier material. Now think about picking up a handful of sand and gravel and blowing on it. Wind is only going to be able to move these smallest, finest sand grains. So when we look at sand, we can usually tell what is the main way that it's being moved around, how much energy went into moving it around just by the grain size. When we have dunes, we tend to have very fine grained sand that is really uniform in size, whereas river sand or beach sands and gravels can be a lot coarser and a lot more variable in size. Now, this park offers this excellent chance to see this geology in action, but it's in memory of a very special event in Oregon's history. In 1970, a sperm whale washed up dead on the beach just in the edge of Florence here. Well, at first this was a tourist attraction. People were coming to see this enormous dead animal up close. Not even just locals, people were driving all the way from Eugene and Portland even to come see it. Well, the catch is that after a while it started to smell super, super bad. So the beaches for much of Oregon are actually under the jurisdiction of the Oregon Department of Transportation. The Oregon Coast Highway took a long time to construct some of the more difficult sections, so historically, the beaches themselves acted as roads for transportation. And because of this, the dead whale was effectively classified as roadkill, meaning the highway department had to deal with it. Well, this is not their normal sort of forte, so the engineers they brought in to deal with the dead whale had the brilliant idea of just exploding it. So they packed the land side of the whale with cases of dynamite. And people gathered all over, sitting in lawn chairs on the dunes, just to watch this explosion of the whale. So they do this countdown to it. They blow up the whale, and suddenly it's not so funny as giant chunks of blubber, rotting whale bits start raining out of the sky. Some of them were big enough to total a car over a quarter-mile away. Thankfully, no people were hit with blubber that size, so nobody was killed or even injured, but apparently everyone watching was covered in sort of a fine mist of dead whale bits. And it makes for a rather amusing video. I highly recommend checking out the video, and in fact, even the Eugene minor league baseball team, the Emeralds, seasonally sometimes renames themselves the Exploding Whales. So it's a really cool piece of Oregon history where we learned what not to do if a dead whale washes up on the beaches.